All right, so as I stated at the beginning of the unit, one of the characteristic reactions that organohalides undergo is in competition with the substitution reaction, and that is elimination. Again, elimination is what occurs when the nucleophile chooses to act as a base. So in a typical elimination reaction, there are three things that happen. Number one, a base removes what's called a beta hydrogen. Now, I'll talk a little bit more about what that means, but a beta hydrogen is adjacent to the leaving group. It would be a very good idea to review your weak versus strong bases. Um, so I would highly, recommend taking a few minutes to do that because that's going to come into play with elimination reactions. Second thing that happens in elimination is that there is a pi bond formed. And then third thing is that the leaving group leaves. Like substitution, the order with which this happens depends on which mechanism predominates. And just like in substitution, elimination has two competing mechanisms. And they're very similar in kind of in style, for lack of a better word, as well as in naming. The first one is E2. E stands for elimination. And again, the 2 stands for the fact that it's bimolecular. And like SN2, the rate is dependent upon both the substrate, so the alkyl halide, and instead of the nucleophile, it's also dependent upon the concentration of the base. And like SN2, it is a concerted mechanism, meaning everything happens all at once. So in an E2, a base is going to pull off a hydrogen next to the leaving group. It's a hydrogen on a carbon next to the leaving group. So here's my leaving group here. And adjacent, if this is the alpha carbon, this is the beta carbon, and the base is always going to go after the beta hydrogen, a beta hydrogen, I should say. When the base pulls off a hydrogen, those electrons move down to form a pi bond. And so that we don't violate the octet rule on the alpha carbon, the leaving group is going to leave. And that creates a pi bond. Now, the other mechanism that competes with this is E1. Again, E stands for elimination. The 1 stands for unimolecular. Those aren't really subscripts. Like SN1, the rate of E1 is only dependent upon the substrate, the alkyl halide. And like SN1, the reaction is stepwise. In fact, the first step of an E1 reaction is the same as the first step of an SN1, where the leaving group leaves. And that's the rate determining step because we're forming a carbocation. Now, after that, the base will pull off an alpha hydrogen, I'm sorry, beta hydrogen, and still form the pi bond. So the end result is the same. You get an alkene. a carbon double bond. It's just the order that that happens is different for E1 than E2. Now I'm going to focus on E2 for right now, and the end goal of this is to start comparing SN2 to E2. Now, we talked about the substrate structure for SN2. The rate was highly dependent upon how accessible the nucleophile was to the carbon with the leaving group. So in an SN2, that nucleophile was blocked if the leaving group was on a tertiary carbon. But E2 actually happens very quickly and very prevalently if instead of being a nucleophile, let's say hydroxide here, acts as a base, it has a much easier time getting to a beta hydrogen than it does trying to get to that carbon with the leaving group. So this is that option was like where the hydroxide basically says, well, I can't act as a nucleophile, but I can still do something. I'll act as a base and I'll deprotonate a beta hydrogen. And in this case, go through an E2 mechanism. Now I'm going to take a little bit of a side trail because we're going to be, I just want to highlight a few things about alkenes that will be important as we go through this unit. So let's talk about how we name alkenes. Alkenes are hydrocarbons that contain a carbon-carbon double bond. And to name them, we're going to use the same rules as alkanes as kind of our foundations, but we change the ending to ENE. Now, when it comes to finding the parent chain of an alkene must contain both carbons of the carbon-carbon double bond, even if there's another longer possibility. So let's look at this, for example. There's a parent chain here, or I won't say parent chain. There's a chain of 8 carbons. However, you'll notice, well, that chain does not contain the double bond in it. So that cannot be the parent chain. So my parent chain is going to be this, even though it is a shorter chain, because both carbons of the double bond have to be involved in the parent chain. And then once we find that, we give the pi bond, the carbon-carbon double bond, the lowest possible numbers, despite where the alkyl substituents are at. And we only number once. So what I mean by that is we don't number the chain to give the alkene the lowest numbers and then reset everything and give the substituents lowest numbers. We don't really do that. Once the numbers are set, they're set. So like, for example, in the above problem, I would give this pi bond the number 1 and 2, and then just continue on like this. So when I go to name this, let's just name the parent chain first. I would say 1-heptene. The 1 tells the reader that the double bond starts on the number 1 carbon and ends on the number 2 carbon. You don't have to put both numbers. In fact, it's wrong to say 1,2-heptene. You would just say 1-heptene, and the reader automatically knows the next carbon over is the end of the double bond. And wherever the substituent ends up with, that's the number it gets. So here on the 3rd carbon, there is a propyl group there. So I'm going to say 3 propyl, 1 heptene. Now, it's also equally acceptable and kind of recommended when we start dealing with like multiple substituents and multiple functional groups. You can take this number 1 and put it in the middle of the name like this. 3 propyl, and then we would say hept 1 ene. So we put the number 1 right before the ene suffix, and that does the same thing. It tells the reader that the um, double bond starts on the number 1 carbon. And as I said before, when we start incorporating a lot more substituents um, and even functional groups, it's going to be almost required to put the location of the double bond in the middle of the name so that there's no ambiguity of what functional group you're talking about. Now we'll kind of go into a little bit more advanced nomenclature of alkenes a little bit later, but I just wanted to give a kind of a quick crash course so that you're aware of how alkenes are named. The other side trail I want to go down is talking about the relative stability of alkenes, because that's going to come up very quickly and how that affects the outcome of elimination reactions. If we are looking at stereoisomeric alkenes, now what do I mean by that? Let's compare trans to butene versus cis to butene. These are stereoisomers of each other because if I take 2 groups, like this hydrogen and this carbon, and flip them around, I get a different orientation in 3-dimensional space. And we talked about this earlier with rings and groups on rings being cis or trans. It's the exact same thing here. But in the case of cis or trans alkenes, what we look at is where these alkyl chains are in relationship to each other. So in trans 2-butene, the 2 methyl groups on the ends are in opposite directions. And in cis 2-butene, those alkyl groups are in the same direction. Now, in general, trans alkenes are more stable. I should say the trans isomer is more stable than the cis stereoisomer. And the main reason for that is simply sterics. Think about these, the carbons at the end, the methyl groups of the end of the butene, on the ends, I should say, of butene. In trans-butene, they're far away from each other. In cis-butene, it doesn't look like it on the drawing, but they're actually kind of encroaching on each other's van der Waal radii. And so when the alkene is cis, it's a little less stable, not a whole lot, but a little less stable because of this sterics. Now, the other thing that affects alkene stability when we're not talking about stereoisomers. So I want to highlight that this first category here, we're dealing with stereoisomers. Same formula, but the atoms are connected differently in 3-dimensional space. Same connectivity. What I want to look at is the number of substituents on the alkene, or what we call substitution. Now, this isn't, I'm not talking about SN2 or nucleophilic substitution. When this is kind of same name, completely different subject. What I'm looking at with substitution is the number of carbons attached to the carbon-carbon double bond. So if we look at this list going from left to right, in this first alkene, there's only 1 carbon directly attached to the double bond. So we say it's monosubstituted. In the next one, there's two carbons directly attached. So we say it's disubstituted. And in the third one, there's three carbons directly attached. And in the fourth one, there's four carbons directly attached to the double bond. Now, due to hyperconjugation, there's that term again, the more carbons there are directly attached to the carbon-carbon double bond, the more stable the alkene will be. Okay, so it's very important to know these two trends when it comes to alkene stability.